Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to analyze the relative motion of a system that's kind of coupled together like this. So let me explain what we're looking at. We've got this bar here that is free to rotate about this point that I called point A. At the instant shown, the angular velocity of that bar is 4 radian per second in the direction shown counterclockwise. Also, we're going to assume this has got an angular acceleration of 2 radian per second, also counterclockwise. This is like a collar that's free to slide along this bar. The collar is connected to bar CD here, which is 0.5 meters long. And some things to notice about this. Because of this angular acceleration, in this angular velocity, we know that this collar also is going to be rotating, and we know that it's going to have an angular acceleration, no doubt. And this point right here will actually have an acceleration along this bar as well. So ultimately what we're going to try to do here is we're going to try to find the angular acceleration of bar CD and the acceleration of point C in what I call the XYZ coordinate system here. Let me explain what I mean by that. I am ultimately going to put a coordinate system right here in this problem, and that coordinate system is going to be fixed to this bar. And then I'm going to work within that set of coordinates to describe the acceleration of C. And what we're going to find is that C is going to have both a velocity vector and an acceleration along this bar. Now this problem is going to be particularly long. I don't think I can do this in under 20 minutes, and I like to keep my videos kind of short. So what I'm going to do is I'm going to start by analyzing just the motion, the velocity of C and the velocity of this bar. And when I get done with that, I'll probably stop it and make another video to talk about the accelerations. Now, if we're going to deal with or look for angular accelerations, you have to start with an angular velocity analysis anyway, because we're going to need the angular velocity of this bar to describe the acceleration of C, because there's going to be centripetal terms. So we're going to start, by looking at the velocity of point C. Now, due to the rotation direction, there is no doubt that the angular velocity of this bar must be this way. So I'm going to call that angular velocity CD. It's got some sort of magnitude, and it, based on the direction I've shown that, I'm going to call that minus k direction. In addition to that, this thing also is going to have an angular acceleration. I'm going to go ahead and just put that in the clockwise direction as well. And I have my reasons for wanting to do that that I'll explain later. And when you don't know an angular acceleration direction, just guess. Take your best guess at it and work it out. And what will happen is the plus and minus signs will sort out whether you got those directions correct. So this is going to have some sort of magnitude, angular velocity CD, angular acceleration CD, and I've got that drawn in the minus k direction as well. Now, I've already started citing directions. You technically should have a coordinate system first. I'm going to go ahead and put a coordinate system origin right here. And I'm going to align this coordinate system origin such that the x-axis, I'm going to draw this in green, points this way along the bar. And then we're going to want a y-axis at a right angle, right through that angular velocity there. That's okay. So my y-axis, I'll just do this. It's going to look something like this. So I've got an x, y. Now, I'm not going to draw it here because I don't want my picture to get too cluttered, but also imagine a maybe capital X, capital Y coordinate system which is fixed in space and not rotating. Now, the angle between this bar and the vertical, looks like I forgot to put that in my picture, at the instant shown, we're going to say is 60 degrees. I just want to make sure that's consistent with what I had in mind here. Actually, going to pause this for just a moment. Okay, I'm back. Yeah, I just wanted to double check that was the angle I had intended here when I made this up here. So, okay, 60-degree angle, that's the one we want here. So we're going to start with this. We're going to start by analyzing the motion of C with respect to O. So I'm going to say that I guess I'll start here and get rid of that. Velocity of C is equal to the velocity of A plus the velocity of C with respect to A. Now, A is not moving, so we got no problem there. Now we'll start thinking about velocity of c with respect to a. Now there's a couple things going on. For starters, we've got rotation. So there's definitely going to be a velocity vector that's going to point like this. That velocity vector is going to equal 0.75 times the angular velocity. So I'm going to just put 0.75 meters. I'll put the units last, times 4 radian per second. That velocity vector is in what I'm calling the plus j direction. Now, in addition to that, remember I'm trying to calculate velocity c with respect to a, but at the instant shown, if you look at what's going to happen here, as this rotates, this collar is going to be moving in this direction. So we're also going to have a velocity this way. This is the one I'm going to call the velocity of c in the x, y, z coordinate system. And this is some unknown magnitude at this point. And it's pointing to the left in the minus I direction. All right, so if I go ahead and clean this up a little bit here, so 4 times 0.75, whoops, you know what, I should go back and put units on this, meter per second. And we go ahead and do this product here, and this ends up being 3j minus whatever this is, velocity of c in the xyz coordinate system in the I direction. Again, there, I just brought that minus sign out front, meter per second. All right. So there is a vector that describes the velocity of c with respect to point A here. Or actually the velocity of c in the xy coordinate system is what I should say. Velocity of point A was 0. Now you'll notice that we don't have this quantity here. So so we got to write another type of analysis. And what we can do now is this. We can also say that, I'm going to go back to the color black here, the velocity c can also equal the velocity d, or I should say is also equal to the velocity of d plus the velocity of c with respect to d. Now the velocity of d is 0. The velocity of c with respect to d, we can write, or I should say we can take note, is straight up. C cannot slide along this bar, so at the instant shown, the velocity of c has to be straight up, so I know it's in the plus j direction, equal to r times the angular velocity that I don't know. So that's going to be 0.5 meters times our angular velocity cd, and that is in the plus j direction. Now, there's no other velocity effect. Again, this point can't slide on this bar, so there is no velocity c with respect to d in some sort of coordinate system along this axis here. So this equation here is basically done. So now what we're going to do is we're just going to compare this to this. And the first thing I'll note is the j components. So, oops, I think I want to stop here for a moment. Okay. Went back and I was kind of investigating this here because something didn't quite feel right, and then I realized something, a little mistake I just about made. Remember the set of coordinates I'm working in here is this green, down and right, up and right. So this is the I direction, this is the j direction. This velocity at the instant shown, if I draw the vector due to the rotation of this object, is straight up. And that is not in either the x or y direction. So I'm going to go back here and we're going to have to modify that. Glad I caught that before I got too much further. All right, so r omega is the magnitude of the velocity vector due to the rotation of this bar, and the omega is omega cd. That vector would point straight up. I'm going to go ahead and draw that in here. This is the velocity c with respect to d. Now here is a 60-degree angle. So if I think about this in terms of components, again, 60, that makes this 60. So if we multiply that by cosine 60, we'd get the component that's in the minus x direction. So I'm going to put cosine 60 in the minus I. And if we multiply that by sine 60, we would get the component in the plus j direction. So I'm going to tack on a plus sine 60j. Again, this will now have units of meter per second. Okay, there we go. So let me go back and get rid of this vector now. I don't need it anymore. It's just cluttering up my picture. I just used it to do the sines and cosines, or to take the velocity component, or I'm sorry, take this velocity, which is straight up due to the rotation of this object, and then write it in terms of coordinates x, y. And we get this. All right, next, now we're going to compare this equation to this equation. So I'm going to do this by comparing components here, and let's see, I guess I'll do the j components first. So here we've got a 3j, so I'm going to just put 3, and again, these are in units of meter per second, equals, and I'm going to take a look right here, j component, we're going to have 0.5 omega CD sine 60. And we can solve this equation, again, this is meter per second, and it's meter per second on the right. We can solve this equation for omega CD. And when we do so, I get 6.93 rad per second. And again, this came out positive, so in direction shown. All right, next we compare the I components. So I'm going to take a look here. We got minus velocity c in the xyz frame. We're going to compare that to the I components here. We're going to have minus 0.5 omega CD cosine 60. So equals minus 0.5 omega CD cosine 60 degrees. We can solve this for the velocity of c in the xyz coordinate system, and again, we know this value. If I go ahead and do that, I get, let's see, when I work this out, I've done that somewhere, 1.73 meter per second. I'm going to take a moment here, just pause this, double check that. Yep, okay, that's been confirmed. Now, you'll notice this comes out positive. What that means is that I've assumed the correct direction. So this velocity vector is up and left, or in the minus I direction. That's the only physical way that one could occur. So I'm going to write the results up here and probably just start a new video for the second part of this motion analysis. So now what we know is that omega CD is 6.93 rad per second. It is in the minus k direction, because that's the direction that I've drawn it in, and it came out positive. We know that velocity c in the xyz coordinate system is equal to 1.73 meter per second. That vector points up and left in the minus I direction. Okay, and I think what I'll do here is just call this part 1. A velocity analysis of the motion of this system, and we'll take a look at an acceleration analysis in part 2.